Today I want to introduce the notation for writing function. There are three ways that it can be presented to a person. A function. At the most basic level, which is basic, which means you see it everywhere, right? Is as an equation. As an equation, y is equals to f of x. Y is equals to f of x. Right? At the basic, as an equation, the reason why it's an equation is because of the equality sign. I like it this way because it's everywhere in mathematics. We can make examples with quadratic functions or what other people call polynomials. We'll explain it later. The word polynomial, right? But when you say function, you have to write it like this. Where this guy, the x, is called an independent variable. It's a variable, meaning you can choose it independently. And when you give that independent variable, well, let's speak more about the independent variable. It exists in what is called the domain. All this will make sense in a bit. Now, when you take the value, you are saying f is that which takes, it's a function that is expressed in terms of x. So I choose to look at it firstly from the right hand side and read it. I know one person can say, anyone can say, y is equals to f of x. I know that. But it tends to lose meaning. It is correct to say y is equals to f of x. But when you say y is a function of x, you are telling somebody, you are telling your mind that this is a function in terms of x. Y is, using this word for is that. It is it. It is it. Y is. You can say is equal to a function of x, abbreviated as is. Y is equal to a function of x, meaning it is a function. This f is a function in terms of x. E.g., simply put, and we call this a quadratic function because of the power of 2. We are not discussing nature of functions or what they are called. Let me make this e.g. f of x. This is a function in terms of x. This is a function in terms of x. It is expressed, it's a function expressed in terms of x. Y is a function expressed in terms of x. Example, I'm giving you an example of a function expressed in terms of x. Now, because I've told you that it's expressed in terms of x, this guy here, he can be any letter, will be called a constant. Formally, because he's attached to that in which the function is expressed, will be called a Coefficient. It's just a constant, it's just a value, never changes. It's a fixed constant. Constant means fixed, it doesn't change. You can't choose it. You can't choose it. You can only choose x. X is the variable. You can choose it independently from the domain. That's one way of writing a function. The other way comes from set theory. Where instead of using the word function, two words are normally used interchangeably. Right? Words for f, it's relation. And the other word is mapping or mapping. Map or mapping. Right. You can say it's a map or mapping. That's the other way of thinking about f. Usually when you say function, it is in the form of an equation, right? But you'll see the word relation, mapping, function. You can use them anyhow. You can say this f is a mapping. Now in set theory, your domain of, that's where your independent variables are. It's usually expressed in capital letters X, right? And I forgot to tell you the name of, this is domain for X, right? Here, it is the range. Right. The range. Now, with this kind of notation, your f is an arrow. This is your f. That's your mapping. That's your relation. It's relating. It's telling you that I'm taking values here from a domain and relating them to y in the range. I'm taking values from the set. This is called a Venn diagram in terms of a set view. This is called a Venn diagram. The arrow tells me exactly visually that I've got values of x in here. 1, 2, 3, 4. They don't have to be only values. This is a set. The reason why I'm using capital X is because I'm thinking in terms of set theory. It's X, capital letter X. So my X, my small x, this guy, the independent, which is a placeholder for these values here, is an element. These are elements. 1, 2, 3, 4 is an element because they are contained in a set. A set is a container of big X. See why notation can be confusing. Now in blue, these can also be values. And they don't have to be 4 of them. They can be as many. There's no relationship here. The relationship is defined by F. It tells me how these values are mapped, and I'll show you the mapping itself. In general, we put it here, right? And in red, I'll show you how it's mapped, right? And from here, because I was using blue here, we say y, small letter y, it's an element of big Y. In other words, Y can be Y. The small y, it's an element, meaning these are elements. It can be 1, 2, 3. These guys are independent. Independent. Just like here, where this was independent. Sorry, this was independent. And this was dependent. In other words, we can only get these values through f by the choice of x. Do you see why I like to read it in? Start on the other side. Or you have to say y is a function of x. Now this is the mapping. I'm showing you how it maps. As an example, using Venn diagrams from set theory, 1 could map to 2. See the direction of the arrow. I always start from the x independent. I can choose. F will take, if you choose 1 and you take f, you give it to f, it will produce 2. In this case, it's just an example. This one can be related to this one. And it can be the end of the story. Even if there are other elements. But we are not here to discuss the prescription of f. This will be a prescription of f as an example. I'm just showing you the word relation or mapping, right? Or we can say, oh, 2 is related to 1. F relates 2 to 1. Or F relates 3 to 2. As an example. That's why F is a relation. It relates these numbers from the domain, the independent values, to the values in Y. Now the third way, which is a formal way of writing a definition of F. A formal way which uses an algebraic, a language of mathematics. All this is a language of mathematics, by the way. And all these meanings mean exactly the same thing. Which I will call an algebraic definition. Let me see. An algebraic definition. We say F, now I'm speaking the language of mathematics, is such that F itself, the function, the mapping, the relation. See, I'm using all three. Is such that for all, this is for all, it's an A, upside down A, values of X. Some people say such that X is an element of the real. In other words, I'm thinking of this set as the real. Otherwise, I could say it's an element of X. Or it can be an element of a natural number. In other words, I'm saying X comes from the domain of natural numbers. That is F, is such that for all values of X in the domain, where the domain is X is an element of this set, in which is the domain. These are my domain. because of x. So if you look at this, we represented this as x, it's a domain. This is a domain. If I'm still on the, this is a domain. We're still talking about the domain, x, as an independent variable. Such that value for all values this arrow here is no different from this arrow here. I'm taking values of x, and mapping them as a map now. I'm thinking, when I see arrow, I think of the word map or relation instead of a function. When I think of function, I choose to write it this way, as y is equals to f of x. If you can still see that board. As y is equals to, because I'm using the word function, but I mean relation. Y is a relation in terms of x. Y is a mapping in terms of f, in terms of x. Y is a function in terms of x. That's all there is to it. This symbol is everywhere. Now, you have to understand the statement that is given to you mathematically. Because sometimes mathematics can change the notation, but preserve the meaning, the same meaning as we discussed here. Right? I can give it to you as y. Okay, maybe this will be an exercise. Y is equals to x. You say, where is f of x? You have to know that here, f of x is x. You have to know. Because it follows the first definition there, where we expressed y is equals to a function or relation, mapping, meaning f, in terms of x. It's a relation in terms, that relation is in terms of x. X, small x. X is an independent variable. But sometimes they give you y if x is equals to x. That's how cruel other people can be. In other words, they're lazy to tell you this statement in full. You see, f of x has got to be given to you. Some lazy mathematicians, and they're still correct. They say y is that which depends on x. They're telling you explicitly here. As if they've moved away from the function. They are not saying y is a function. They are saying y is directly related to x. To some people, it may mean two different things. Y is a function of x, where a function of x is equals to x. This is a short form, is a long form of this. This is a short form of this. Even lazier mathematicians will give it to you like this. y is equals to x. Meaning they're implying this notation. It means y is related to x. The formal definition of mathematics is that it's a function in terms of x that relates the values of the domain to the values, to produce the values of the range. They have said it correctly. F is a mapping that takes as input. I'm gonna write it in red, maybe in green. Input, the independent guys, it's like an input to produce an output. You have to understand these three things because they mean exactly the same. This way of doing things in terms of the concepts of set theory is great because it's visual. You can picture the X, the domain. You can picture it. Here is a picture. It's two circles with numbers inside. The numbers inside are called elements of the set. Set is usually denoted by capital letter X. That's one aspect of it. Now I have to stress this concept of y is equals to f of x. Y is a function of x. Y is a mapping in terms of x. Y is a relation in terms of x. In all these ways, because they all mean the same thing. I'm only saying why. This is a formal algebraic definition. This one. It's a formal algebraic definition. And I might have made an error somewhere. A formal, using the language of algebra being, giving us the expression, how we call the name. Like for instance, let me label them in red. Like for instance, this is the weight such that. This is the weight for all. For all. This means element. This means now, it means mapping. Relation. As in relationship. It's talking about F. F is such that for all values of x, where x is an element of some domain, meaning it can be real numbers, natural numbers, or x, big X. Maps the values of x to the values of y where y, sometimes they don't even write where, the word where. It's an element of, now it can be anything. It can be the years, it can be big Y, it can be natural numbers. F is a mapping. F is a mapping. It's a function. It's a relation. F is a function. The very same F. It's a relation, a mapping, which tells you how I'm mapping. It says this number 4, F maps the number 4 from the domain to the number 3 in the Y. It's a mapping, it's a relation. It's still a function. However, people, when they say function, they usually think in terms of that formula. I don't know, that equation. Some people call it a formula equation. I don't know what is a formula. I don't know what is an equation. Now it gets the last point that I want to mention. Because the notation can be very confusing to other people, even to me. It can be very daunting, right? Now, I was thinking something else, and now I'm writing blue. I forgot what I wanted to say anyway. And I will remember after switching off this video. I will remember. So, everything that I've written here, you can simply write it as y is equals to f of x. You don't have this, you don't have to write this diagram, but if you come across this diagram, it means y is equals to f of x. Just that here it's emphasizing the word relation. It's telling you how things are related. Okay, two things that I wanted to remember. Now I remember the second one instead of the first. Right. You see that? I'm telling you that F, it's a relation. It's a function. It's a mapping that takes two independent variables, x and y. It needs them. You have to choose two. It's like baking a cake. The inputs needs two inputs to produce something that depends on these values of x and y. These two values, x and y. Now, mathematics says, hey, I've run out of alphabets. X. Now, I want a function that depends on 10 variables now. Independent variables. X, Y, Z. Now I'm done. Should I say A, B, C? Or I say A, B, C, I use them as constants. Right? It changes the notation. It says, why don't I index my independent variable? Index them using a subscript number, 1. Sometimes it starts with 0. X2, X3, X4, X5, let's say 5. This is a relation, this is a function that takes as input 5 inputs, independent. It's like baking a cake again, where you need your x, maybe it's x1. You say, I'm going to represent eggs as x1, milk as x2. The amount of milk, the number of eggs, you will give it a value. You have a choice of the number of eggs. It depends how many cakes you want to bake. Butter will be x3, maybe. Water will be x4, and x5 will be heat. How much temperature? You see? It's a total representation of reality. To produce a cake, now what do I call a cake? In this case, because I've released the use of y, I can say to produce a cake, the number of cakes, the choices of these inputs will produce this in the range. The range is how much can you produce, how much output can you produce. You pour petrol in a car, You can choose your variables to say how big is the capacity of the engine. How much speed were you using? These are inputs, independent, because you can choose them. You can travel at, I don't know, 120 kilometers per hour or 240 kilometers per second. It's up to you. Or the speed of light. That will be another input to produce the power of the car, the velocity of the car, the acceleration of the car, how much power, whatever you want to represent your output as. Physics. And I'm sorry for doing this to you because I'm stressing the point of F, showing you that it can depend on more than one variables. That is perhaps mathematics for college students. Now, physics at high school, F for force is equals to MA. But they tell you at high school that A is a constant acceleration. Now, M is the mass of the body, doesn't change. When a car is moving, doesn't change its mass. Does it? Doesn't. For physics, is this the same F that means the function? This one means force. But physics can change life drastically for you, where it remembers that actually acceleration, mass never changes of a body. I weigh whatever kilograms. I can change if I eat something maybe by 1 kilogram, but as I speak, maybe I can change also. But I normally don't change. Like a mass of a car. Maybe it changes because the petrol consumption changes. The acceleration is the rate of change of velocity. Now maybe you've never seen that operation before. This dv by dx, right? In particular, the operation that operates is called d by dt. It's called the derivative. And it can get worse. At college now, this was up to high school, where A, acceleration is treated as a constant. So it's a multiplication of two constants, mass and acceleration. But at college, things can change. When now velocity, that's even more. Is expressed in terms of position, x. That force is dependent on the second derivative of x in terms of t. So x itself, x and v are functions of time. You see, now I'm using a different f, means exactly the same thing. I'm telling you it's a relation that depends on time. Meaning time is independent. Exactly like that. Exactly like everywhere here. We used x here. Now I can't use xx. It won't make sense. X depending on x. I can depend on myself, but I need food, I need water, I need oxygen. You see? You don't have to listen to this part, by the way. I'm just connecting things. Position, displacement, sometimes they call it displacement, a change of position. As a vector, they even put a bar here. That's physics now, to call it. tell you that it's a vector. It's a function. Whichever way they put it, it's a function. They might as well have said f is equals to mass times a function of time. Formally. Now, if physics can write this for me in this way, so that it connects with mathematics, I will love physics. But until then, good luck. End of lesson. 35 minutes.